let's take a look at fission and nuclear reactors. So fission is the act of splitting a nucleus into smaller nuclei and releasing energy in the process. And this process, this fission process, can be either spontaneous or induced. Spontaneous just means that it happens by itself without any outside influence. So in a spontaneous fission, we would have a large nucleus like this, and then it would split into smaller nuclei, plus some random assorted little bits over here. An example of that would be the spontaneous fission of uranium-238. Now, this is not a common thing for uranium-238 to do, but it can spontaneously break down into strontium-95, xenon-140, and 3 neutrons. Now, fission requires you to have a somewhat unstable nucleus to begin with, because you don't want a very tightly bound nucleus, because a tightly bound nucleus is unlikely to split. So if you were trying to cause fission to happen, one way to get fission to occur is to create an unstable nucleus. And the easiest way to do this is to add a neutron. The reason why that's the easiest way to do this usually is because a neutron has no charge. So as opposed to a proton, where a proton would have to overcome the Coulomb repulsion if you sent it into a nucleus, a neutron has no charge and it can just fly into the nucleus. However, it can disrupt the forces inside the nucleus. It can disrupt the balance of force between the Coulomb repulsion and the strong force because the neutron adds some strong force in the nucleus. So the easiest way to get induced fission is to have neutron-induced fission, where you send a neutron into a nucleus and that causes a fission to happen. So for example, neutron-induced fission of uranium-235 would look something like this. Uranium-235, you send in a neutron, and then it fissions into barium-141, krypton-92, and also 3 neutrons. You can also have neutron-induced fission of plutonium-239, and there you get fissioning into a barium-143, strontium-95, and 2 neutrons. But in each of these fission reactions, energy is released, and the energy can be released in the form of the kinetic energy of the products that come out of the fission reaction, or it can be emitted as a gamma ray. Now notice for the neutron-induced fissions that we looked at, a neutron is used to cause the fission to occur, and it also results in more neutrons coming out. So this can lead to a situation like this. Imagine we send a neutron into a, say, uranium-235 nucleus. It fissions into 2 things and releases 3 neutrons. Those 3 neutrons go off, and they impact 3 more uranium-235 nuclei, which then fission. And each of those releases 3 neutrons, which then go on to cause more fissions, and so on and so on. So by the 3rd generation, 13 reactions have taken place. By the 5th generation, 121 reactions have taken place. By the 10th generation, 29,521 reactions have taken place. By the 50th generation, 3.59 times 10 to the 23 reactions have taken place. By the 100th generation, 2.58 times 10 to the 47 reactions have taken place. So this idea is called a chain reaction. The first reaction creates products which then cause more reactions, and so on and so on and so on. Now this view of fission has overlooked a lot of details. In reality, not every neutron causes another fission. Many of the neutrons that are emitted in a fission reaction escape without causing another fission. Also, in most fission reactions, there are 2 related problems. Number 1, the neutrons which are emitted by fission reactions have high kinetic energy. They emit fast neutrons. Number 2, to cause another fission, the neutron must be slow, or a so-called thermal neutron. And that might seem a little bit odd, because you might think that a high kinetic energy neutron would carry a lot of energy into a nucleus and do a good job of splitting it apart. However, fast neutrons essentially just fly through the nucleus. They go into the nucleus and then they come right out. So you need a slow or thermal neutron to impact the nucleus to cause a fission reaction. So to get more fission reactions, we need a way to slow down the neutrons which have been emitted in the fission reactions. So when attempting to cause a chain reaction to happen, often we introduce a material near or within the material undergoing fission, which can slow down the neutrons. This kind of a material is called a moderator. A moderator is a material which is able to absorb energy from fast neutrons, which remember cannot cause fissions, and turn those fast neutrons into slow thermal neutrons, which can cause fissions. Common moderator materials are water and graphite. Graphite is just a fancy crystalline form of carbon. So now we're going to think about how to take these ideas and turn it into a power plant. We're going to look at a simple model for a nuclear power plant. So we're going to start out with the nuclear fuel rods. These nuclear fuel rods are usually concentrated uranium-235. Now, when I say concentrated, I don't mean that it's pure uranium-235. It's usually just a few percent uranium-235, but that's enough to get a fission reaction happening. The second thing we're going to add in is a moderator, and here we'll put water around the fuel rods. And water, remember, as a moderator, will turn those emitted fast neutrons into slower thermal neutrons, which can then cause further fission reactions. Next, we will add control rods. These are made of a material which is able to absorb neutrons like cadmium or boron. And the idea with the control rods is that they can be either inserted or removed from between the fuel rods. And this allows the controllers to adjust the rate of fission. If they're lowered down between the fuel rods, then they'll absorb more neutrons and the rate of fissions will decrease. And if we remove the control rods, then fewer neutrons will be absorbed and the rate of fission will increase. In most reactors, the thermal energy that's coming out of the fission reactions is used to heat up water. And then the water is pumped out from the reaction chamber, and this extraordinarily hot water is used then to heat up another set of water in a part of the power plant called the heat exchanger. The heat exchanger is literally a place where heat is exchanged between the very hot water that's come out of the reactor and another container of water right here. This secondary water is then usually allowed to boil, and once it boils and turns into steam, it then passes through a pipe and goes over here and turns a turbine. That turbine, when it spins, then generates electricity. After the steam has passed through the turbine, it usually goes through a cooling pool and turns back into water. Sometimes this is called a condenser. And then that water is then sent back over here to the heat exchanger, where the water from the reactor heats it up again and turns into steam and turns the turbine. And then, of course, up here, that hot water that came out of the reactor, then after it has transferred some of its heat in the heat exchanger, it's now a little bit cooler, and that cooler water is sent back into the reactor, where it continues the cycle. The last thing I'm going to add to this diagram is shielding. The reactor is shielded in some way by concrete or lead or iron or some material which prevents radiation from the reactor from getting out into the world. Notice that the water that is in the reactor never leaves the reactor. It is in a closed loop. The water that's inside the reactor and all the material that's inside the reactor is not allowed to interact with the outside world. The only exchange is an exchange of energy. So that water never leaves the cycle. It transfers energy through the heat exchanger, but the water that is in contact with the reactor never leaves that closed loop. Now eventually the nuclear fuel rods use up the uranium-235. The uranium-235 contained in them undergoes fission, and there's not enough uranium-235 to be used as fuel rods anymore. These are called then spent fuel rods. And what's left in these spent fuel rods are the product nuclides from the fission reactions. And often this is stuff like barium, krypton, strontium, cesium, iodine, xenon. The nuclides that remain in these spent fuel rods are not stable. They often decay by beta decay, and they have half-lives of varying lengths, sometimes seconds, sometimes hours, days, even years. Another problem is the escaping neutrons from the fission reactions and the radiation from the products can be absorbed by materials within the reactor. So for example, the casings and the fuel rods or the machinery surrounding the reactor. And this can cause those to become radioactive. So for example, if we had aluminum-27 in the fuel casing inside of the nuclear reactor, and a neutron is absorbed by this aluminum-27, it will turn into an unstable aluminum-28 nuclide, which then decays into silicon by beta- radiation with a half-life of 2.25 minutes. The spent fuel rods and the radioactive materials inside the core altogether are referred to as nuclear waste. So nuclear waste contains isotopes of varying half-lives. It contains the byproducts of the fission reactions, and it contains nuclides from radiation bombarding material that's inside the reactor. So the question is what to do with it. Immediately after it is removed from the reactor, it's usually left in a pool of water. And this is done so that the pool of water can absorb the beta or alpha or gamma, hopefully, radiation that's coming out of it. And it also allows it to cool down that nuclear waste. And the reason why it has to be cooled down is the radioactive decay, which is happening in the nuclear waste, is heating up the material. If we emit beta radiation, for example, that means a high energy either electron or positron is being emitted, and that high energy electron or positron is going to deliver some of its energy to the surrounding atoms. That will give them kinetic energy, which means that their temperature will increase. So the pool of water gives it a chance to cool down and also for the water to absorb some of the radiation that's being emitted. After a while, that nuclear waste is removed from the pond, and then it's put into a steel or concrete tube called a cask. And some countries have organized long-term plans for these casks. Some countries have long-term underground storage for them. And some countries have something called reprocessing, and the idea here is that some of the spent fuel rods can actually be turned into new fuel, which can be used again. We're not going to go into that idea very much, but just know that that's an idea. In the United States, the casks are almost always stored on site, and in the description for the video, I will provide a link so that you can see some of these casks in Google Earth. There was an idea for a national central safe storage facility called the Yucca Mountain Facility, and it was conceived of in the 1970s and 1980s. It was approved in 2002. However, this was supposed to happen in Nevada, but Nevada residents were quite concerned about the safety of this. There was also concern from people who were going to live near the transportation routes for the nuclear waste. And the project was defunded in 2011. The Government Accountability Office declared that it was defunded because of political reasons, but it depends on who you ask. Opponents would argue for less risk tolerance. So the people who were opposing this idea were asking if it was too risky. They questioned whether this facility would be safe enough in the long term. And they were asking, is the risk worth the benefits? And that's a difficult question for many reasons. It depends on what your risk tolerance is, and that risk tolerance might change depending on if you're a person who's living somewhat close to the facility versus someone who's living on the other side of the country. And science, of course, can't answer those ideas about risk tolerance, but science can provide the information for us to make an informed decision.